Welcome to our third installment of the discussion on Alex's paper called The Limits of Mathematics for Mortals and Immortals. Did I say that correctly?
Yes.
Yeah, I said it correctly, yes. In this episode, we are going to cover two sections. We're going to cover the second death of mathematics, and we are also going to cover the third death of mathematics. We're going to talk about some physics, and then we're also going to talk about some book recommendations in this actual episode. So it's kind of like... perhaps it'll be somewhat like that show Reading Rainbow, but for nonfiction books. I'd be very, very excited to do that, in fact. I think that would be an awesome thing to do. So for the sake of our audience, let's go ahead and talk about a little bit of what we talked about in our previous episodes.
So we finished off with the Kurt Gödel theorem saying that mathematics is incomplete, that there are theorems that you know are true, but they require potentially an infinite amount of time for a computer or some mechanical system to prove the theorem.
Correct. So it is not something that we can use to prove all theorems. And then in this, actually, I don't want to jump ahead of myself. Was there anything else to...
We're going to continue with the next consequence of Kurt Gödel's theorem.
This is an exciting one. Just looking at our table of contents here, just for a little preview of some of the stuff that we're going to talk about here. Let's see here. So the second death of mathematics starts off with Paul Cohen and his contributions, then gets into a section called the insanity of the Banach-Tarski paradox. That is something that is definitely worth searching on YouTube. That one is a mind-blowing paradox. I can't wait to get more into that. We then have a section called Were the 2 years of research worth it? Where Alex spent 2 years doing a lot of research into these paradoxes, and we'll find out what he learned in those 2 years. Perhaps we'll save you some time. We then get into the third and more deaths of mathematics. It's almost like there's an infinite number of deaths of mathematics, perhaps. And then we talk about something called the End of Insight, which you may or may not be familiar with, by the famed author, mathematician, and professor Stephen Strogatz. And then we get into physics and even more deaths of mathematics from Morse Klein. And then finally, we're going to talk about a book here. Mind if I hold it up? Mm-hmm. This lovely book, which is exactly what we've been talking about, but into much more depth. So we will talk about this book and recommend it as a nonfiction book. So... all right, without further ado, let's talk about Mr. Paul Cohen. Who was he and what were his contributions?
So Paul Cohen was a mathematician who did his work in the 60s, and he did his work on the idea of looking at the axioms of mathematics that are fairly successful in describing today's mathematics. They're called the Zermelo-Fraenkel axioms, and they're very simple axioms, and you adjoin something called the axiom of choice, which I think Wikipedia does a really good job of describing. And he was able to show that you can't guarantee consistency of mathematics. And let me back that up to a problem that lasted roughly 2,000 years. It was the problem of the fifth postulate of Euclid. And Euclid said, Euclid's fifth postulate was that two parallel lines never meet. And mathematicians for roughly about 2,000 years felt you should be able to prove that two parallel lines never meet. And of course, they failed for roughly 2,000 years. Around the 1500s, a mathematician named Zachary began to experiment. He said, well, let me make the lines meet at infinity, or let the lines diverge at infinity, and let me create a new kind of geometry. And he did. He created different kinds of geometries. The results were absurd. I mean, he would get results like the interior angles of a triangle are no longer 180 degrees. How? See, that's physically absurd, because in the real world, the sum of the interior angles of a triangle is 180. He died thinking that he had exonerated Euclid, that he had finally gotten past that problem. He died not knowing that he invented non-Euclidean geometries, which is kind of funny. And what's funny to me is that if you look at a globe and you see the latitude and longitudinal lines on it, you have a geometry that's equivalent to plane geometry, except it's on a sphere, and they weren't aware of that.
Yeah, interesting.
So pardon me. What Paul Cohen did is he did similar things. He said, well, what if I take out this axiom of choice? What if I include it? And there's some other axioms. What happens? And he began to discover that the result of this is that our choice of axioms, which most of mathematics is built from, cannot guarantee consistency. So imagine you're a ninth grade student, you're studying plane geometry, and you're going to prove theorems for 1,000 years. And there is no guarantee that you're going to always be consistent. In other words, you may derive a theorem that was logically derived from the last 100 years and derive another theorem, and they're inconsistent with each other. They actually contradict each other. There's no guarantee of consistency. And so that's what I would call the second death of mathematics.
Wow.
Loss of consistency.
Yeah. Interesting. Oh, and then this is, I think, probably one of the most exciting parts in my mind of this section is discussing the Banach-Tarski paradox. Where did this paradox come from, and what exactly is it?
So it's the Banach-Tarski paradox is a consequence of the Zermelo-Fraenkel axioms with the axiom of choice. It's a strange one. It says you can take a solid sphere and you can decompose it in such a way that you take the pieces and you can assemble two copies of the spheres with no gaps. Same size. It's an existence theorem, so it doesn't tell you how to do it, but it tells you that it can happen. There's nothing wrong with the proof. It's within the Zermelo-Fraenkel axioms and the axiom of choice. That's a weird one. That's part of the problem that we've realized, that it's hard to create a set of axioms that doesn't have these kind of weird paradoxes, and of course they're not guaranteed to avoid inconsistencies.
Yeah, I think there's a lot of resources online that I'll include links in the video for examples of this. I think there's even several YouTube videos that try to show a good picture of it as well. So lots of cool stuff on that. So let's talk about these 2-year period of research that you did. In this section of the paper, I think we can go ahead and read it directly from the paper right here. It says, were the 2 years of research worth it? Tell us when did you do 2 years of research into this, and what were you looking for?
So at the time, I was a young man. I was a lieutenant in the Air Force here at Kirtland Air Force Base. And this is how I was spending my nights. And I've always been interested in what the limits of knowledge are. And, I spent 2 years beginning to study the history of Fourier, as we discussed in the last episode, all the way through Kurt Gödel and Cohen here that we've just discussed right now. And I think it's worth it because lots of people are always wondering, what's the limits of what we can know? Mm-hmm. And, well, as you discussed, there are a lot of limits of what we can know, including, we think of mathematics as a perfect science. And I think we've shown that it has many defects. It's one of our most powerful tools for understanding existence. It's good to know what its limitations are. So I thought it was well worth it.
Okay. So right here it says, were the 2 years of research worth it? And it says, no. At least not in the sense of making my operational proficiency in mathematics any better. Of course, then you correct yourself. Well, I shouldn't say correct, but then you clarify. You say, yes, however, and develop me frame certain kinds of existing thoughts. Interesting. So that sort of solidified for you that...
You're right. You don't have to... It doesn't make you a better mathematician. It doesn't help you solve differential equations or complex variables. What it does is it binds... if you're thinking about a civilization that's arbitrarily advanced, well, they're still stuck with these problems. There's no technological solution, wait a million years, for some civilization to figure out a workaround. These are fundamental limits.
Wow, that's cool. Fundamental limits of all time, all societies.
And I would think they apply to arbitrarily advanced civilizations and any kind of deities that humans have conceived so far. These are fundamental limits.
Wow, interesting. So then we get into the section on the third and more deaths of mathematics, and you start this section off with the question, will computers usher in an age of scientific authoritarianism? And you just answered that in your previous comment about these eternal problems. The very first section here is The End of Insight by Stephen Strogatz. That was a paper of his, or was that a book of his?
I cut and paste a discussion he had online, and it's on this paper. It's literally a quotation from him in some journal I found years ago.
Yeah, I think there's a few things that are worth reading directly from that, if I may. Stephen Strogatz himself says, I worry that insight is becoming impossible, at least at the frontiers of mathematics. Even when we're trying to figure out what's true or false, we're less and less and less able to understand why. And I think that quote comes from the solving of the four-color theorem. Can you tell us a little bit about the theorem itself?
So that's an interesting theorem. I think it was finally proven in the 1970s, and it was done so with computers. The idea is, how many colors do you need so that when you're making a map, an arbitrary map of countries, that no two nations have the same color? If you use 3 colors, there are maps out there that you'll have country A and country B abutting each other on a border, and they'll both be blue. So what's the minimum number of colors you need so that never happens, which is a very practical problem? And the answer is 4. And the proof required a very large computer and a large amount of time to go over a very large but finite set of combinations. And that was the proof that we need 4-color theorem. Strogatz's point of view is, in that time, from the 70s to now, roughly 50 years, no one has found a human readable proof of that. We have to accept this proof from this computer, and so it becomes authoritarian. The computer says so, and that's what he's worried about. And it's happening more and more often. Another one is the classification of finite groups. That's another one that required a computer, and it doesn't seem like there's any path to a human-readable, human-derived version of these theorems. And of course, as computers get faster and we get better at using computer proving systems, it's only going to become worse. The computer says so. There's no questioning. It's of the authority of the proof by the machine.
Okay. Now, I think from a previous conversation we had on this topic, you said you are not as worried as Stephen Strogatz, or rather you have a more optimistic outlook. Is that right?
I talked to one of my good friends at Sunday National Laboratories, who's a mathematician, and he's not as worried about it because he says, we understand all these foundational issues. We understand the fact that in some cases computer proofs are the only way to go. But we're going to be practical about it. We're going to ignore all of that. And we're going to say, if we're studying a system of differential equations, what we're going to do is we're going to use algebraic topology or other tools to, if not perfectly find the solution, bound the solution, characterize it and bound it to where it can, as best as we can. So press, in other words, as they say in the Air Force, press.
Yep, press on, right? Okay.
So let me add something a little bit to Strogatz. This is a chemistry problem. There's a tool that came out between 5 and 10 years ago called Chematica. And Chematica ingested all organic chemistry reactions ever from the literature, and there's millions of them from what I understand. And it's able to do something that humans can't do because we're so limited and finite. It's able to study the chemistry of dyes, the chemistry of petrochemicals, the chemistry of drugs, all the literature all at once. And it was able to find, I think in 6 cases, reactions of high importance to the pharmaceutical industry that are very complicated. They take many steps, and the computer was able to read the literature and go, there are one-pot reactions to get your drug. In other words, it read the literature on paints and on dyes and on this and that. It said, you just put all these ingredients together, shake it, and you get your drug, instead of the very complicated path. Now, no human could read millions of papers spanning more than 100 years of organic chemistry to have found these solutions. But once the solutions are found, they're like, oh, well, they're logical and they can be explained. That's a little bit different than the 4-color problem. The 4-color problem, you're stuck with it, no human proof. At least in the chemistry sense, the computer, says stick all these ingredients together, and you can go to the laboratory and go, wow, it works. So that's an interesting thing that I wanted to bring out. That maybe we don't need chemists or physicists because the computer is just going to come out with the solutions.
That's incredible. I had no idea about that. That is actually really, really awesome. Wow. And this is just us scrolling on our paper.
Right. So I think the next section that we're going to get to is the End of Physics Reductionism.
Okay. Very good. Yeah, and we've already touched everything here on the chem thing. So
I think we've pretty much gone through all the mathematics, all the limitations and that mathematics suffers just because of how you construct it.
Okay.
So go ahead.
So in this next section, we just talked about chemistry. We now are going to talk about physics and possibly the end of physics reductionism.
Right. So this is a really interesting idea. It's relatively new to physics. We like to think of a building as composed of, say, rooms, and then if we go and take a wrecking ball to the building, we'll find out that the building's made out of bricks. And if we take a wrecking ball to the bricks, we find out they're made out of molecules. And if we take a wrecking ball to the molecules, we'll find out it's made out of atoms. And then we'll eventually smash the atoms and find out it's made out of protons and neutrons and electrons. And that's reductionism, right? We're going backwards and backwards to more fundamental units. And eventually we get to the quarks, and that's where we are right now.
Yep.
Go ahead.
Oh, I saw a comic about this, actually. I don't remember who did the comic, where it had two cavemen who were arguing about obviously it's fictional. It's two cavemen arguing about fundamental particles, and one of them said big rocks are fundamental. One of them said no, smaller rocks are fundamental, and they smashed the rocks together and said, okay, you're right, smaller rocks are fundamental. So kind of the same idea, but like how deep do you want to go?
It is the same idea, except here in the physics of our universe, we have electrons. We don't have the equivalent version of a particle for magnetism. Magnetism is a derivative result of electricity in motion, creates magnetic fields. But there's no reason why Maxwell's equations couldn't contain a particle that's responsible for magnetic charge. Mm-hmm. So in the 1920s, Paul Adrien Maurice Dirac invented a theory of magnetic monopoles that's still relevant today. And what we began to realize is in his theory, the electron begins as a fundamental point particle, and the magnetic monopole is a string that's infinitely long. And what we've begun to learn is if we change the strength of the strength of the electric field in favor of the magnetic field, the electron becomes more and more spread out in space-time, and the infinite magnetic monopole becomes tinier and tinier. And in the limit, we can get a point magnetic charge particle and an infinitely long string for the electron. What is the fundamental particle? Once you can do that, that's the interesting point. That physics itself, especially if you think of multiverse and other universes, there may not be reductionism at a certain point. There may just be a tuning of parameters.
Interesting.
So there are no bricks. At a certain point, what's more fundamental, as you were saying? The big rocks, the little rocks. So what's more fundamental, electrons or magnetic monopoles? Neither.
Wow. And then this may be tangentially related, but I guess I'm curious then, when you factor in the Planck length, or do you say the Planck length, depending on your pronunciation, that sort of throws things into a loop as well, because, what does that say about fundamental particles and fundamental energies? Like you can't even measure anything that is smaller than that. So it's sort of a moot point, would you say?
Yeah, I think physics at that scale, we're very, very far away from playing there.
Fair enough. Very good. Yeah. And then we've got this last section here on Even More Deaths of Mathematics by Morris Klein. This is where you get into the book right here that we're talking about.
So Morris Klein here, he was a mathematician. I think this book was published in 1980. And this is really the book. If you've been listening to the podcast, this is really the book that gets into all the deaths of mathematics and in the history, and the literature search in it is fantastic. So I would. This is a book, unlike last time, I would totally recommend.
Awesome. Yeah, and this book was published, in the 80s, right?
Yeah, 1980, I believe.
There are so many outstanding books that were published in previous decades. I feel like a lot of the newer books get the attention, but not on this podcast. On this podcast, we'll talk about books, that are great books, regardless of when they were published. So, who would you suggest this to in terms of their background? Would you suggest somebody maybe who is,
anyone who's got a little bit of calculus and as a background and is interested in, I don't know if you've been out of school for a while, but you've had some calculus. If you're in school and you're getting a technical engineering degree or a math degree, this is a very good book to frame your understanding of mathematics.
Nice. In the very least, let's say that you went to college and got a degree in art, but you're very interested in this kind of stuff. With the help of Google and Wikipedia, hopefully it should be pretty good. Okay, cool. Very good. Now, interesting. So in this section, you bring together a whole lot of ideas here. In the introduction, you specifically say that the aforementioned Zermelo-Frankel axioms, as well as Gödel's incompleteness and the Barber's paradox, go into the innate limits of mathematics as we try to construct upon a perfect, or you said a Platonic ideal plane foundation using set theory and logic. But these are only the tips of a bad iceberg. Or of bad icebergs, rather. In this book right here, Morris Klein goes into far more detail into the cracks of mathematics. I really like that introduction. That was very, very well written. So some things should be read out loud, I think. First thing you ask is math created or discovered? That's a fun one.
Yeah, that's a big debate. Is it something that is a human invention or invented by civilizations, or is it discovered? And that I don't know. I tend to go either way. In a sense, it doesn't matter. But if you say that 1 and 1 is 2, fundamentally, did you discover that or did you invent that? If you say on a plane the interior angles of a triangle are 180 degrees, did you discover that or did you create that? And of course, it gets deeper into, as mathematics gets more advanced, are we creating mathematical technologies to solve like differential equations, which are practical to the real world? I don't know, but that's an interesting debate that mathematicians often have.
Interesting. And then you say, what is Brown, in parentheses, topology to the rescue?
So Bertrand Russell of the Russell Alfred North Whitehead book, The Principia, that we discussed previously, he really went deep into the idea of what math is and what reality is. And right now we happen to be sitting before a Brown table, and he asked, what is Brown? Because as the sun has been changing angles, the spectrum that's going into our eyes is changing. And you and I are different people. What makes us agree that it's Brown? And so he really, I think, got off the deep end, and this is personal opinion. This is where I tend to get off the bus and not really listen to the philosophers and go more with Richard Feynman, who's just practical. He didn't appreciate philosophy. In later discussions that I've been working on machine learning and artificial intelligence, the idea of what is Brown, if you get on your computer and you do Wikipedia Brown, what's it going to do? It's going to present to you brown animals, dirt, brown pants, brown hair, and those are all topologically linked. So Brown is a bunch of linkages in our brain, and that's how we all agree. That's what Brown is. So I think that averts practically the philosophy of what is Brown.
Wow. Interesting, yeah. And then this next section is called Euclid was not even... I love my job. My job is to read the section headings. So your job, it's okay. I love how much effort you've put into this paper. It's incredible. It was a huge Herculean effort on your end. So I am perfectly fine being the guy who reads the headings for now, for this episode. So this next section here says, of course, Euclid was not even wrong. I like the phrase, such and such or so-and-so was not even wrong. That's not usually a compliment to those people.
That's a Wolfgang Pauli physicist. I guess I would call it an insult.
Okay.
Your stuff is not even wrong.
Yeah.
So leave me, in other words.
Yeah.
This really is material that was derived from the mathematics the loss of certainty by Morris Klein that we've just discussed. And it goes on to nitpick, Euclid. Euclid, you say you postulate points and you postulate lines. And if you really start being careful, what is a line? You have to define it, topologically. Is that in between any 2 points there's a point? Are you guaranteed that that's true? You have to worry about, that's any line segment is already as big as the big infinity. Mm-hmm. You can map all real numbers to that. So that's the idea that the Euclid was not even wrong, because he wasn't even realizing how fundamentally we just implicitly assumed, of course, straight lines, let's go. Mm-hmm. That there's a lot of depth to that. There is this problem right here, this famous problem here of if you take this infinite sum, 1 minus 1 plus 1 minus 1 plus 1, keep going, alternating signs, mm-hmm. You can show, Daniel Bernoulli, in fact, in the 1700s showed, you can make that sum to any number that you want. You want it to equal to a half. There's a way to rearrange the terms in a clever way, and you get it to it's a half. You can rearrange the terms in a different way and get it to be 1/3. So there's an example of a lack of inconsistency if you're not careful. Mm-hmm. You have radically different, you have an infinite number of results possible from 1 plus minus 1, plus 1 minus 1 plus 1. It's really kind of funny, and it's cleared up by being more careful with your axioms.
Yeah. Wow. Interesting. That's next section here. So in this next section, we're talking about how Einstein's, and we are at the section of what is. It gets a little meta there. It gets a little self-reflective. In this section, you talk about how Einstein's theory of general relativity is a generalization of the Newtonian gravity consistent with small corrections to small deviations between Newtonian gravity and experimental observations. General relativity, however, is descriptive. It doesn't tell us what gravity is.
Right. People always, they like to ask physicists, well, what is gravity? And the answer is, I don't know. Mm-hmm. We can describe things. Theories are very good at describing. They don't tell you why or, what it is fundamentally. And I think one of the papers I want to emphasize here, it's hard to find, so please go to the website that we have available. It's put up there. Sure. Is John Archibald Wheeler, which I think he was the graduate advisor of Richard Feynman. He wrote a paper, Law Without Law, how the universe can exist, create life that observes itself and defines itself. It's kind of a heady paper. It's I think it was written in the 1950s, and it's out there. It's hard to find, but we have it posted.
Mm-hmm. We'll include that as well. It'll be we'll have a link on the show notes, also on our website, which should be touringrabbitholespodcast.com.
Right.
Yep, we're still working on that.
So the next thing I think is how many types of numbers are there? And does that limit how much we can know? And if you start off with numbers like 1, 2, 3, 4, 5, the counting numbers, they're very useful for counting how many marbles you have in your pocket or dollars you have in your wallet. But they're not necessarily good for business. If you owe money, there's no negative numbers.
Yep.
So then you expand from natural numbers, the counting numbers, to the integers, and now you can owe money. Mm-hmm. You can have negative money or debt. How do you show ratios? Well, with fractions. So you begin to expand your numbers. Mm-hmm. Now, what's interesting about counting numbers and integers is that there's a whole gap between 1 and 2. There's a discrete jump. When you get to the rational numbers, it's always possible to find between, say, 1/2 and 1/3. It's always possible to find a fraction between those two fractions ad infinitum. And you would think, well, that if you take a microscope to as you fill in the fractions between fraction A and fraction B, in the middle of that, in the middle of that, you would think you're going to get a smooth line. No, that's the small infinity. In fact, you don't have a line. You just have an infinite collection of zero measure, and now you need the real numbers. And the real numbers are that larger continuum we discussed last time, where you have numbers like pi that are transcendental. We've been building larger and larger number sets to solve more practical problems. Counting numbers are good for counting, and then the integers for business, rational numbers for ratios. By the way, that's how the Greeks bypassed the real numbers. They said, we're not going to worry about real numbers. We're going to just call everything a ratio. And then we get to the real numbers that glue in the missing gaps, as we discussed. But of course, you can't solve a simple problem like x squared is equal to -1 without imaginary numbers. And in physics, imaginary numbers are very useful. They are useful for describing processes which have friction where the energy dissipates. After that, up until this point, all the numbers have had what people say are nice properties, and properties that you come to expect. 2 plus 3 is the same as 3 plus 2. That's called commutativity. And all the numbers we've discussed have that nice commutative property. Now, around the late 1700s, early 1800s, people began, I think late 1600s, early 1700s, people began to try to find a system of math numbers to describe 3 dimensions. And things that we call vectors in the x and the y and the z direction, as we think 3 orthogonal axes, they were stymied by the fact, eventually discovered by Sir William Rowan Hamilton, that you have to give up commutativity. There is a kind of vector multiplication called the cross product, where A cross B is not B cross A. It is the negative of B cross A. And so that was the beginning of, okay, we've been successfully growing our number systems to solve more and more problems, but now we've just lost commutativity, a very nice property, if you want a mathematics to describe vectors as we do in physics. If you continue up that, there's one more system of numbers which is very useful by physics. It's the quaternions, and it's really a four-dimensional idea. It's really the idea that instead of having just the imaginary I, now you have an imaginary j and an imaginary k, and they roughly line up with the x and the y and the z axes. In fact, you can do vector calculus with these numbers. In relativistic particle physics, they describe the electron and the anti-electron. The electron can have a spin up or spin down, and the positron, the anti-electron, can have a spin up or spin down. So the quaternions are very good at that. Of course, you lose some more properties. There's a number system called the octonions, and every time you jump up, you're losing properties that are nice. And eventually you're getting to number systems that we don't think have any physical usefulness. After octonions, I think there's one more number system, but finding its meaning, and it's so hobbled by how many properties it's lost. What's interesting to me is you run out of number systems that are useful.
Interesting. Wow, this gets a little trippy. Wow, sorry, I'm trying to think of a great way to summarize all that, and it's just nutty. I mean, this is where you get into some really creative sci-fi shows, like one of my favorites, you know.
Yes.
I always bring Rick and Morty with the dimensions, and then you think of like, is there like an infinite amount of math systems? You know, like it just gets trippy. I can't even think.
I definitely think that there is a limit to more sophisticated, more complex number systems, where because they're increasingly complex, you lose too many properties. Losing commutativity is okay because you didn't really lose it too much. The A cross B is anti-commutative.
Mm-hmm, mm-hmm. That's right. Interesting. So in this the paper, you wrote a heading that I think is it optimistic or is it pessimistic? You say, "Who cares about all this death? Carry on with life."
If it's not optimistic, it's at least practical.
Okay, I like that.
So it's the notion. If you think about it, life is written in four letters, right? A, T, C, G at the DNA level. Mm-hmm. And if you got four letters and look at the varieties that we have throughout the last few billion years and where we are today, you can do a lot with limited systems. Mm-hmm. So you're not going to build a rocket ship with DNA. You're going to build humans that are going to build a rocket ship with DNA. So there's emergent properties. So in that sense, I'm not too worried about the deaths of mathematics or the fact that number systems eventually get so complex they become not useful.
Okay. Yeah, interesting. So yeah, I mean, again, we've gotten pretty far with engineering, and it still certainly works. I mean, we're able to communicate on our iPhones and our Androids, so that's it's certainly quite
Correct.
Useful, even if it's not perfect, even if the Platonic ideal does not exist, it is still certainly a wonderful thing that we are all very grateful for.
Right, and the Greeks ran into a whole bunch of impossibility theorems, right? Squaring the circle, trisecting the angle, with a straight edge, and what was it? The straight edge and compass, right? Mm-hmm. And there are things that took a couple of thousand years to prove. You cannot prove certain theorems using only straight edges and compasses. Okay, so invent a different curve. So that's something called the tomahawk. Please look that up. Not the weapon used by Native Americans, but a tomahawk is a curve, a more general curve that lets you trisect the angle. There's another impossibility theorem that's very famous. If you have a polynomial of fifth order, there is no formula for that in general. If you remember high school, you think there's a quadratic formula for solving quadratic equations.
Yes. There's
a cubic equation for solving any cubic polynomial that you may be presented with, and there's a quartic formula for any polynomial of order 4. In general, if you have a fifth order polynomial, there is no formula for it, and that was the beginnings of group theory in the 1830s. And so, what do? Well, you invent something called elliptic function theory to find solutions to quintics. You always grow the math beyond the set of tools. When you hear an impossibility theorem, in the Greek sense, it's because they were using straight edge and compass. In the sense of polynomials, is because people were using factorizing polynomials, and you get to a point where you can't distinguish roots, and it's a group theory problem. So you invent more math on top of that. Mm-hmm. So there's always workarounds to mathematics.
Fascinating. And that's something that I will say this straight up. In high school, the first time that I did algebra a couple of times by choice. I didn't have to, but by choice. I did it again in college because I was just curious about it. I did not always connect what I was doing algebraically to actually, graphically what's going on. And the minute that I saw an ellipse with two foci versus, a circle with a single foci, it all made so much more sense. I was cranking out the mathematical sausage of Algebra 1 and Algebra 2 without even realizing it. And I just feel like the most immense light bulb went off when I saw some of the graphics. That's why this day and age is so exciting. We've got the YouTube videos like 3 blue, 1 brown, and everything else that just shows these beautiful visualizations. There's also a math page I follow. It combines mathematics and art, and they show a lot of algebra problems with colored blocks, and it makes so much more sense now. Goodness.
Definitely. You bring up a great point. I think the way we've been teaching physics and math can be improved so much with, graphical methods and presentations. And it definitely extends beyond it. There's if you want to look at the impossibility, I would search YouTube for impossibility, the quintic Galois theory.
Right.
And you'll see visual representations of why that can't be solved with the old-fashioned ways.
Yeah. Also, again, not quite that level, but let's say that you're a high school teacher. I would definitely suggest looking up not only the proofs on YouTube, but any proofs through pictures. There's some wonderful ones that just do a great job of explaining this mathematics, things that I didn't have when I was in high school. So kind of a golden era of education in some ways.
I think so.
Yeah. Now, in this paper, back to the paper, we get into a section called Limit Workarounds Through Creativity Within N and Certainty for N plus K. Can you tell us what that means?
This was just me musing. Science fiction author Arthur C. Clarke, who is credited with inventing the satellite, or at least the idea of the satellite, said that after a certain amount of time, a civilization will get so advanced that to us, they might appear like they're magical. And they're simply way ahead of us. And I was just thinking in terms of like Chematica. With Chematica, the organic chemistry tool, would that seem like magic to organic chemists 100 years ago? And I don't know if it would or wouldn't. If we imagine Leonardo da Vinci, who invented flying machines in principle, if we showed him the Wright brothers flyer, it kind of looks like what he would draw in his sketches. Yeah. He would be not surprised at all. Mm-hmm. However, if you present him with an F-22, pulling G's and Mach 2 on the ground, he might think, wow, that is magic. It's just this idea of trying to understand how far we can predict into the future. Probably 5 years from now, the world's going to look pretty much the way it does now. But how about 500 million years from now? If assuming civilization continues on, how magical will it look like? And how good can we anticipate the arbitrary future?
Yeah, that's a very good question. Fascinating question. Yeah, that's fun musing. Okay. Alrighty. So what I kind of like is that I'm looking at the paper right now. We are barely at the halfway point, and we are at the end of this episode and at the end of the third death of mathematics, and there's still so much more to go. What excites me is that for our next episode, we're going to take a break from this paper, and we're going to talk about something else. We are going to talk about civilizations and stability. And once again, earlier we did a little bit of a book recommendation. I think we can do another book recommendation, namely because our next episodes will be inspired by these books, as well as a paper that you wrote after reading these books. Is that right?
Yes.
So again, we have more papers from Alex. But yeah, let's do a little preview starting with a book recommendation.
So this is called War and Peace and War. It came out maybe 10, maybe 15 years ago by Peter Turchin, who's an entomologist. And he developed mathematical models for insects and then decided to turn these models towards human dynamics and specifically from the Roman Empire through right around the 1900s. Mm-hmm. And he in the second book here, Historical Dynamics, he developed a system of statistical differential equations that capture roughly statistically between the fall of Rome and 1900 in Europe, how many city-state empires, how many empires would pop up, what their size would be, how long they would last, And I think it's a great idea to try to capture statistically, where's the world going. I think governments today would like to know maybe how stable certain countries are going to be, when they might rise or fall. So it's very interesting. In addition to that, the paper I wrote covers the use of statistical physics to try to predict avalanche behavior. When the Arab Spring happened, one man burned himself in Tunisia, and that event, which we'll get into in more detail, led to the toppling of many dictators across in the Arab Spring area. What causes that? What causes that? We'll get into that. There's something called the forest fire model. There's self-organized criticality and I'm blanking here. Let's see.
Oh, it's okay.
We'll cut
Forest
it out.
fire, self-organized criticality. Or you just say those two for now. I know it's not perfect, but it's just a preview. And many others.
Okay, here we go. And self-organized criticality and catastrophe theory that tells you when something's going to have an avalanche behavior.
Yeah, fascinating. So, yeah, what I love about this podcast, not only are we going to do deep dive topics about math and physics, but also about the human condition and society at large. And obviously, it's very, very inspired by mathematical models, so we're not completely escaping math. But, still some great questions. So, like and subscribe, or I would rather say, please, if you enjoy this video and you enjoy this content, like and subscribe. You can like us on Facebook, facebook.com/Turing Rabbit Holes Podcast. Also, you can find us on Discord. I'm trying to get a better Discord name, but that option is currently not available at this time. So I will put the Discord link in the notes. You can also email us at touringrabbitholespodcast@gmail.com. We would love to hear from you. Send us your questions. We'd love to do some read aloud of the questions and some Q&A. We love to interact with our audience. Also, if you leave a review for our podcast, it would mean a lot to us. You can go to anchor.fm/touringrabbitholes. Also, the other links I just provided as well. So we'd love to hear from you, and thank you for your support. Stay tuned for our next episode.
Thank you.